Yeah, probably online. Excellent connection. Everything's reloading for me. Yeah. All right, I can see myself in the corner. I put it down to a low quality video, amount, so as not to stress your connections, but we'll see. Hey everyone, it's your boy ChemistNate coming at you with another banger. Today's banger is me sitting here answering your questions, if you have any. I recognize there is no one here right now, but that's fine. It's my first one. Maybe it's the middle of summer and you don't have chemistry questions. Whatever. I'm going to sit here and be here for you, because that's the name of my game. We do have 6 viewers, it looks like. If you have questions, paste those questions in the chat. I will copy and paste those questions into this Google document and then help you answer them. I don't really have a way for you to talk at me with audio. I could give you my phone number, but I'm not going to. It does look like we have a couple people here. Again, if you have chemistry questions, paste those questions in the chat. Oh yeah. How to find quantum numbers. Ooh, I like that. Is that, I'm going to guess that that's either from an electron configuration diagram or, tautomers. I have had a quick question here about tautomers. I am not great with tautomers except for enols, and I honestly am not sure that I'm going to be able to give you any better information than what you could find from probably another chemist. I'm weak. I haven't seen tautomers in quite some time. Okay. Arzu Bichu Mach 18. So I'm going to go over some quantum numbers first. One of the most common questions I see about this is like finding the 4 quantum numbers for the final electron of, some element. We can go with oxygen to start. Oxygen's a nice, easy one. The idea here is that you can figure out the electron configuration for oxygen probably on your own. Arzu, correct me if I'm wrong, but if we asked you for the electron configuration of oxygen, I'm hoping you'd be able to come up with 1s2, 2s2, 2p4? Yeah, I think it's 4. The idea being that you have 2 electrons in the first subshell. That's actually the first shell. And then the first subshell of that. By the time you get to the second energy level, like n equals 2, or the second circle in a Bohr-Rutherford diagram, the 8 electrons that you can fit into the second shell are actually split up into 2 subshells. There's an s subshell, which can hold 2 electrons, just like the s subshell of energy level 1 could hold 2 electrons. And a p subshell that can hold up to 6 electrons. Now oxygen, however, is element number 8 on the periodic table. So we actually only want 8 electrons total in the neutral atom here. Oh, it's not going to respond to me. Element number 8, there we go. The little superscript 2 here tells you that it has 2 electrons in the first shell, 2 electrons in the 2s subshell, and 4 extra electrons in the 2p subshell. 2 and 2 and 4 make the 8 electrons. Now we could draw a diagram for that too if we wanted to. It might just be easier if I go and track it down for you. Electron configuration diagram of oxygen. Only bringing this up so you can see it in a second way. Wow, I think my computer's lagging badly. Oh well. Hello, everyone who's just saying hello. You're all good people. Thanks for joining me. Perhaps I should break this up into different types of chemistry. Now here's what I'm talking about. Let me check my streaming software, make sure you can see that. Yes, you can. Here we've got 2 electrons in the 1s subshell, 2 electrons in the 2s subshell, and 4 electrons in the 2p subshell. Now, what you'll have seen in my video about electron configuration is sometimes I'll bring up an order of filling. If you want a diagram like that, Google order of filling, and you'll learn what order to fill these subshells in. But for now, I'm just going to copy that. Nope, I don't want the link. I want the image address. Thanks for bearing with me, everyone. I got a bunch of questions rolling in here. We got stuff about ligands. We got limiting reactants. I'm just going to paste that diagram in there. Ah, nuts. It's an SVG. Shh. Yoink. There we go. There's your diagram. Okay. Now the question was, how do you find the 4 quantum numbers for any electron? You may be dealing with an electron configuration or an electron configuration diagram, but hopefully you can see that the superscript 2 is for the 2 electrons in the 1s box. This 2 is for the 2 arrows in the 2s box, and this 4 is for the 4 electrons in the 2p boxes. Okay, so here's where it gets awesome. You're asking about the electrons' quantum numbers. The final electron that would have gotten added here is this one, this down arrow inside the first 2p box. I know that's the final one because it's the 4th electron that we added to the 2p subshell, and you're supposed to spread your electrons out before you double them up. I believe that's the Pauli exclusion principle. Aufbau is bottom up. Hund is... Oh no, Hund is spreading them out before you double them up. I don't know, whatever. The point is, this down, you're supposed to put 1 electron in each of these boxes before you ever pair 2 electrons up. All electrons are negatively charged, and so they're going to repel each other and will only pair up if they're forced to. Put 1 electron in each subshell before you double any up. Okay, so the final electron in this example is this down arrow. It is, I'm going to make that note here so you can see it. Wow, computer, final. This happened on Zoom while I was teaching high school last year. Final electron is the down arrow of the 2p subshell. Okay, the 2 tells you the first quantum number. The energy level that the electron is in is straight up the first, or principal quantum number, n equals 2. The p is what's going to give you the secondary quantum number. Most people here in North America call it little l. I think it's secondary quantum number. It's the subshell number. On a chalkboard, I'd be using a cursive L so that you can tell that it's lowercase. But hey, what are you going to do? Now, P represents 1. You're basically going to have to remember that. An S subshell has an L of 0. A P has an L of 1, a D is 2, and an F is 3. That's basically what you're, like the limit of what you're going to see. If your teacher is really trying to challenge you, you keep going in order. You do G, and I've actually never in my life seen a question that asked you for H. By the time you get to G, you're way beyond wherever like the actual periodic table takes you. Mach 18 contributes the fact that you call it the azimuthal quantum number. That rings a bell in my head, but I stopped calling it that quite some time ago. Okay, now here's the best part, if you ask me. You already know that L is 1 because it is a p subshell. What we say is that the third quantum number, ML, or the magnetic quantum number, can go from negative L to positive L. But I find that a lot of teachers don't show you what that actually means. The MLs, which here go from -1 up to +1, correspond to each of the boxes in the electron configuration diagram. The first box from the left, at least I go left to right here, we give an ML of -1. The second box is what gets an ML of 0. The third box is what gets an ML of +1. This rule that chemists invented for ML, where it goes from negative L to positive L, is how we explain the fact that all of the 2p subshells can hold 6 electrons. Because you can fit 2 electrons in -1, 2 more electrons in 0, 2 more electrons in +1. So, this ML has 3 possibilities. Since L is 1, it can be -1, 0, or +1, and we usually label them from left to right, from lowest to highest. The first box has a -1. Now, if you were in a D subshell, you would have gone from -2 to +2, and you would have had 5 boxes in the D subshell. Any electron configuration diagram where you get up to 3D, I guarantee you will have 5 dashes or 5 boxes for you to put electrons into. The last quantum number is really just about whether or not your arrow points up or down. The fact that it's a down arrow, I call that an MS of -1. I could imagine some teacher somewhere getting those backwards. When you do upper level quantum mechanics, it really doesn't matter which quantum number you assign to which electron, as long as one electron gets the proper quantum numbers. And the spins are more for how the electrons interact, and so it's their sign that matters. Now, someone pointed out just now, we actually call this -1/2. It is either -1/2 or +1/2. That comes down to upper level quantum mechanics on why we do that. There's no real reason for it. You just have to memorize it. That's the way we go. So, here's my recommendation if you're asked for all 4 quantum numbers. Draw yourself the electron configuration and probably the final part of the electron configuration diagram so you can see where your final electrons are. This gives you N and L. And counting through the boxes produced by your MLs will tell you whether or not your final electron, of these 4 in this case, are in which box and which way the arrow points. What up? Absolutely beautiful. Thank you for your question. I hope that provided you with something. Now, before I try my best to explain tautomers, I'm going to copy in some of these extra questions. Someone said how to do limiting reagent questions. That's the third one here. Copy, paste. Legacy, retracted your message. Oof, what can you do? We've got ligands and coordinate covalent bonds. Coordinate covalent bonds, you're just going to have to sit tight, I guess. It's probably going to be past 11:30 by the time I get there. Two unpaired orbitals, radicals. Someone wants me to explain radicals. Someone asked me where I'm from. I am from Canada. Here in Canada, we have summer break for high school teachers right now. That's why I'm free to help you in the middle of the day. If I wasn't with you, I'd be trying to trade some stocks. Someone's asking about radicals. Chanel, hope I got that right, asks about rate processes. I'm going to need you to be more specific. If you have you're kind of asking me to go over all of kinetics there. Perhaps it's coming up with the rate law for something from a table of some kind. We'll see. And lastly, we got intermolecular forces and electrolytes. Okay, Mach 18, you've asked for fluxational molecule concept. I'm not going to lie, I have no idea what that is. I've never heard of that in my entire life. I'll Google it when I get there. And maybe it's just called something different here, right? Cool. Okay. Quick explainer on tautomers. I am not great at these. The only experience I have with them are things called enols. It's going to be better if I show you a picture here. I don't have a way to draw these molecular formula whatevers. Okay. Okay. So, what we've got here in this picture is a double bond next to an OH group. Now, the two pictures I'm highlighting on your screen right now are the same molecule. This carbon has two hydrogens on it, which are not shown. This carbon has, well, actually that looks more like a quaternary. Anyways, you have a double bond and an OH on one of the carbons that has the double bond. Here's the idea behind enols, is that you could remove the H away from that. Now that's just resonance. I don't know what a tautomer is. Nope. Nah, it's been so long, I don't remember. Thank you for coming by. I don't remember. Let me study, please. Mach 18, you've been asking me the toughest questions so far. I'm not confident that I can even answer what a tautomer is at this point. It's been so long since I've seen it. I do promise you that I'll reteach myself tonight and crank out a couple of videos for you later today. I'll write that down as homework for myself. But I can't help you. Sorry. Nothing like radical honesty, I suppose. Okay. Now, it does feel like lots of you are studying for a high-level test right now. Limiting reactant may not be the kind of question you came for. Someone dove in. I just want to run through a quick one here. Let me come up with something here. Let's pretend that we are reacting magnesium solid with, I don't know, let's just use oxygen gas. And it becomes MgO solid. Now I chose that because I knew there would be coefficients. And I'm choosing two different states as well. Limiting reagent is asking which of the two reactants is going to run out first. Magnesium is a solid, so let's say we have, I don't know, 20 grams of it. I know many of you are going to be worried about significant figures, so I'll call it 20.0 grams of it. Come on, computer. We're still having some struggle. Lots of you are having a blast in the chat. I'd like to see that. I'm going to have to scroll up to go see what other people asked. And I'll say we have, I don't know, 60 liters of O2 gas at STP. Now it's a gas, so I'm going to have to give you the temperature and pressure, which I do here. Okay. In order to figure out which element or chemical of the two reactants limits you, you have to convert all of those reactant amounts. Come on. Oh, I got such lag. Convert each reactant amount into moles. The reason we have to convert to moles is because it's how we count molecules. And these coefficients sitting in front tell you how many of each thing react with the other thing. So the first step of a limiting reactant is going to be some kind of formula. For the solids, you can simply do number of moles equals moles over molar mass. Sorry, grams over molar mass. Now the formula I use is little m over capital M, whatever. Little m is the mass. This is 20.0 grams. The molar mass of magnesium you can get from a periodic table. It is 24.302. 24.302 grams per mole. Use as many decimal places as your periodic table gives you. You know what this calls for? This calls for a little bit of calculator work. Bam. 24 divided by 20 grams divided by 24.302. Now, I turned the resolution down on my camera, but you might be able to see what I've typed. 20 divided by 24.302. When I do that math, it gives me the number of moles. The grams cancel out because I'm dividing them out. This is 0.822978. Now, I personally keep lots of decimal places until the end. It's just how I do things. And I'm going to note to myself that that's the number of moles of magnesium. Now, to calculate the number of moles of oxygen, I've got a couple options. Because it's a gas, you may prefer to use little n, number of moles, equals PV over RT. That's pressure times volume divided by the gas constant times the temperature. But you also have another way to do it. You can take the volume that you have and divide it by little v, the molar volume, at whatever temperature and pressure you were given. Not sure if you've seen this formula before, but I like it. Capital V, the volume, is 60 liters. And the molar volume at STP is 22.4. Now, molar volume is measured in liters per mole. Again, if you don't know what molar volume, or little v, is, you can use pressure times volume divided by gas constant times temperature. PV over RT. That's the ideal gas law. This, though, is a nice little shortcut. I like it. Someone asked, yo, are we doing stoichiometry? Yo, you betcha we are. Someone asked for it. I'm just going in order. When I do 60 divided by 22.4, I got 2.67857 moles. Very nice. Now that's of O2. Now, once you've converted each one into moles, you might have an idea of which one is limiting. But I personally do one extra calculation to figure out which one is actually limiting. I divide each number of moles by its coefficient in the balanced chemical equation. Whichever gives you the lowest number here is limiting. Now the person whichever gives you the lower number here is limiting. The person I teach chemistry with at the high school I teach at does this a different way. They convert this to moles of MgO that would be produced. They also convert this to moles of MgO that would be produced, and then pick whichever of those is smaller. It's also a valid way to do it. But for now, I'm going to do it my way. For Mg, I take my 0.822978, and I divide it by 2. That 2 comes from the balanced equation that I had before. It's the number in front of it. Oh, yeah. Do it on your calculator. 0.411, 489. Now that's actually the number, well, doesn't really mean anything, I suppose. It can sometimes represent the number of moles of something that's produced, but not today. O2, that coefficient was actually 1. So I just take this number and divide it by 1. Will my computer select it? Yes, after 5 hours of work. So, take each of the number of moles that you calculated and divide it by the coefficient on the balanced chemical equation. Whichever of those numbers is smaller is limiting. Now what you're probably being asked for in most of these questions is the theoretical yield of one of the products. We only have one product here, that's MgO. So here's what you're going to do. You're going to take the number. I swear I'm a better typer than this. Take the number of moles of your limiting reactant and you're going to multiply it by the mole ratio. I'll show you what the mole ratio is in just a moment once I fix all of these errors. I can tell my computer's lagging. When I was teaching high school last year, or it was last year, I typed so quickly that it lost some of the keystrokes and put a swear word on the screen in front of everyone. What can you do? So I have my number of moles. Now be careful. You're actually using the number of moles here. This is 0.822978 moles of Mg. And you're going to multiply it by a fraction. That fraction will always be the coefficient of the thing you are asked to calculate. In our case, it's MgO. That's 2. And if you want a unit, it's the number of moles of MgO that you make for every. And on the bottom of the fraction, you're going to put the coefficient of the thing you are calculating from. In our case, it is solid magnesium. We agree that it is the magnesium that is limiting. And you make MgO from Mg in a 2:2 ratio. Oh yeah. Someone's saying your time is precious. That's right. And so if you feel like this is going a little slow, you could always leave and then come back. Who knows? When you do that multiplication, you end up with some number. This one happens to be easy, but we've converted it to moles of MgO. This is the theoretical yield. You calculate theoretical yields from the limiting reactant amounts. Now I gave you two numbers, each with 3 significant figures. So you have to round this as well. Now I like using a wavy equal sign for my approximately. Your teacher or school probably has a special way that they want you to show that. I'm kind of lackadaisical when it comes to that. I use this curvy equal sign for approximately equal to, and it's 0.823 moles. There's my answer, but again, convert all your initial amounts into moles and then divide each of them by the coefficient from the balanced chemical equation to figure out which is limiting. Go back to that chemical's number of moles and use it to get the theoretical yield. What up? Very nice. Okay, we got a quick question here about ligands. Ligands are chemicals or ions that attach themselves. Attach themselves to usually a charged central ion or atom. And the way that they're held on is generally intermolecular forces. I say intermolecular because it's not a permanent bond. Sure, they can move around the water or whatever they're in as a unit, but they're pretty easy to pluck off generally. It's not a full covalent bond. You can call it a coordinate covalent bond, but it's really just like an ion dipole attraction. The most common example of this, which I'll bring in for us, is NaCl. When you dissolve salt in water. Well, that's more solvation than anything, so let's not use that. I was just thinking about stuff like this where you have a central atom and then stuff is connected to it. Let's just use hexa, aqua, chromium. Yeah, sure. Is that a thing? Yeah, that's what I'm talking about. This would have been a Cr3 plus ion to start, but that's a lot of positive charge in one place. And water molecules, just like carbon monoxide molecules and most ions like Cn-, have a plus and minus side. They have a dipole. Here, the negatively charged side of a water molecule is attracted to the strong plus charge of the Cr plus 3. There we go. Each of the waters has delta minus partial charges on the oxygens and delta plus charges on the waters. If you're looking to see how that works, I can just bring up water dipole here. Oxygen is more electronegative then hydrogen. So you end up with something called a dipole moment. You may not have to draw that in there. Most people here in the school that I teach at just show these delta plus and delta minus charges. Now these exist for most of the things that can act as ligands. Oh, my computer's having a bad time. Another popular ligand is carbon monoxide, or CO, carboxy. Well, come on, computer. Is Cr kind of holding the molecule together? Yes. More accurately, it's the positive charge on Cr that is causing all of these other things to be attracted to it. If I bring up a picture of carbon monoxide's dipole, you'll see that it also has a plus side and a minus side. No, it's carbon dioxide. Get out of here, computer. There we go. Well, that one actually has a different formal charge, but whatever. The point is that there is a plus side and a minus side. Oh, computer, stop crying on the inside. Let me know in the chat if you can hear the fan on my computer going absolutely ballistic. The idea is the plus charge of the chromium here is holding everything together. The electron pairs of the oxygen will almost attach to the chromium, but it's not a full covalent bond. In fact, I guess I could explain that as well a little here. So, an electron pair from, in this case, oxygen, will attach. And I do emphasize, it is kind of temporary. The H2O can get displaced by any other particle that either happens to be present at a higher concentration or is hungrier for the positive charge of the chromium. I'm imagining maybe an ammonia. Don't quote me on that. I haven't memorized the order of like ligand hungriness or whatever. But it's not a permanent covalent bond that is very difficult to break. It's an attachment. It is temporary. And it's happening because the O has a slight positive charge and the Cr has a strong, the O has a slight negative charge and the Cr has a strong positive charge. Opposites attract to the center. And it is those waters, by the way, that make them ligands. The ligands are the things surrounding the strongly charged thing in the center. Now, the other thing I'm going to point out here is oxygen brought both of the electrons that make that temporary bond. The oxygen brought both of the electrons that make that temporary bond, which is how I explained that it is coordinate covalent. The electrons are still being shared in there somewhere, but oxygen brought them both. It was not a perfect covalent bond where each of the atoms brought one electron. Oxygen brought both. That is why we call it coordinate. Now it's a covalent bond here because the orbitals on chromium are actually changing to help accommodate it. That's above my pay grade. I don't exactly know how that works. Either I slept through that lecture in university, or they just never taught it, and I would have had to take a more specialized course. But every time you talk about ligands, I want you to talk about the central atom, which probably has a charge, and the dipole on the ligand itself. Now, there are a couple examples. I believe fluoride and chloride can act as ligands and attach to stuff. Chloride ligand example. These are attracted simply because they have a minus charge. Yeah, look at that. We got a cobalt surrounded by ammonias. The N has a small minus charge. Yeah, here we have chloride ions being attracted to a cobalt. But again, they are bringing both of the electrons for that temporary covalent bond. That's why it's called coordinate covalent. Very nice. Someone asked a question about radicals. You know what? I'm being inspired here to whittle down the subject because I feel like we're all over the place. Some of you are responsible for radicals and some of you aren't. Radicals in general are chemical species with an unpaired electron from somewhere. The easiest way to make these is to start with a dihalide, like Cl2, chlorine gas. And if you shine UV light on it, you'll break the covalent bond perfectly. You'll end up with a Cl atom with one electron that is unpaired. I guess I should be clear. That chlorine atom will have 7 electrons total. That's an odd number, though. Oh, no, I don't want that. I want dot. Nope, I want circle. There. That's how I'm going to show my radicals here. Did that work? Yeah, it did. So, the single bond between the two chlorines, breaks apart perfectly. 1 electron goes to each of the atoms. Now they each have 7 electrons, but one of those electrons is unpaired. Electrons do prefer to be paired, so these, and by that I mean radicals, are reactive. In the case of these Cls, this is how we get some polymerizations happening. You can get a chlorine to react with an alkene. It becomes a radical. It reacts with another alkene. It becomes a radical, and over again. Yeah, someone says unfilled valence shell. Someone says, are we going to get a recorded session video of this? Yeah, I think I get the option to just make it public. You'll be able to find it on my channel later. As long as YouTube hasn't changed how I think they're doing things. Your question is just like radicals. Not sure what much more you would want than this. This is also the thing that breaks apart ozone in the atmosphere. That Cl. There we go. Reacts with O3. You end up with, I believe it's ClO. Oh, what am I doing? Printing? Someone said cool. I assume I answered your question. ClO. You get oxygen gas instead of ozone in the end. That's ClO. Oh, come on, computer. Wow, I do not remember this at all. Can react with another ozone molecule. Does it make ClO2? I don't remember. I really should, though. The real point I'm trying to get at here, whether or not I'm actually correct, is that the chlorine can react with other things and prefers to, because that unpaired electron is trying desperately to get another electron to pair with. Then that passes its unpairedness onto something else, and then it passes its unpairedness onto something else, and it ends up being a catalyst for lots of different types of reactions. Don't quote me on that. You'd have to look up halogen-catalyzed ozone depletion to get the actual mechanism, and for all I know, in the past 10 years, it's changed. Someone's asked about rate processes, and they later clarified that they wanted rate laws. And then I'm going to Google fluxational molecule concept to see if I actually know it by another name. Okay, here's the idea behind rate laws. Chemicals must collide to react. And multi-step reactions require many different collisions. Now, molecules are... I swear I typed that right, and I actually typed the whole word. Multi-step reactions require many different collisions. But molecules are moving around so quickly, as long as you're in either the gas or liquid phase, that you can usually count on the collision to happen eventually. The whole idea with rate laws is you figuring out which step of a multi-step reaction is slowest, which chemicals are involved with that step. And how do their concentrations affect basically the effectiveness of the collisions? I'm going to use the word good here. A good collision is one that results in a reaction. I'll put that in quotes, scare quotes, to make you feel like there's something else going on there. So, something like H2 reacting with Cl2 in the gas phase. There's not much more that can happen between these two than for them to hit each other at a particular angle and swap where the electrons are in a precise way to produce two molecules of a new thing. In order to make that happen, the H2 has to collide with the Cl2. Now, I don't actually know what the mechanism or list of steps is for this reaction. Let's assume it's a one-step reaction. What that means is that in order for this reaction to work, you're going to need an H2 molecule and a Cl molecule to collide with each other, like a hydrogen and a chlorine molecule. Only one H2 is required for this collision, so we generally put an exponent of 1 on it, and we say the order of reaction with respect to hydrogen is 1. You only need one of them in this collision. It's the same for chlorine, and again, we are simply assuming that they collide with each other, mono a mono, one on one. Now, rate is measured in something else. It's like moles per liter per second or some other concentration unit per second. We end up having a rate constant to make sure that the units and numbers work out. Whoever just asked about zeolites, yeah, I got nothing for you. I know what they are, but I don't know anything about their properties. Okay, dude, relax. Oh, it's not letting me mute you right off the bat. Maybe it'll let me mute you here. Yup. You just need to chill out there. Okay. The idea is we have 1 and 1 reacting together. The order of reaction with respect to H2 is 1. The order of reaction with respect to Cl2 is also 1. It is pretty rare for you to get orders of reaction more than 2, but it is technically fair. Okay, that dude is gone. I am done listening to that. Put user in timeout. Is that a thing? It's fun. It's my first day, so I'm learning. I can also just hide the user if I want to. Oh yeah, message deleted. Look at me. I'm hilarious. Dude, I got nothing to say except I don't know anything about zeolites. And we say the overall order is 2. That is the sum of those exponents. Now that overall order happens to also be the number of molecules that are colliding in the rate-limiting step. You can also have order of reaction be 2 with respect to one single thing. I'm trying to think of like a chemical reaction where 2 of the same thing react with each other. Yeah, I can't right now. I'm real rusty on that. But I have seen stuff where the exponent on a single thing is 2. The implication there being that the rate-limiting step is probably 2 Cl2 molecules colliding with each other, but things do get more complicated once you involve multi-step reactions. Other teachers will often give you 0-order chemical reactions. I don't know, I'm just going to make something up here. Let's go with O3. Let's say O3, or rather, literally anything that decomposes in a linear way. It's usually nuclear, radioactive things decomposing that end up being 0 order. You're just eating away a constant amount of something. I forget what I was saying there. These are just the most common things. An overall order of 1 means that one of those molecules is probably involved in the rate-limiting step, or is involved in a step that feeds the rate-limiting step. An overall order of 2 represents 2 molecules colliding in the rate-limiting step, and I've seen teachers ask about 0th order as well. Now, the last thing that I want to point out is that if you have, say, 3 things reacting together, let's do Br2 plus, oh, goodbye computer, H2. This is not a real reaction either. But let's say we make HOBr out of these things. I know that's not balanced, but sue me. The rate-limiting step probably does not involve all 3 of those reacting together at the same time. Getting two molecules to collide with each other happens all the time, but having three in the same place at the same time reacting at the right angle is rarer. Most teachers will tell you it's possible, but getting four things to collide in the same place at the same time is fake news. Hardly ever happens. Here, the rate is likely to be something that relates to two of these chemicals. Perhaps it's the H2, exponent 1, and Br2, exponent 1. The order of reaction with respect to O2 here is 0 because it's not involved. If they told you the rate law was this tells me that the rate limiting step is likely a collision between H2 and Br2. That itself tells you that O2 comes in probably afterwards, but it can also have simply reacted really quickly at the very beginning. It's not that O2 is not involved at all, it's just that it's not involved in the rate limiting step. So if you were to propose a mechanism here, you might propose that H2 and Br2 react to make some HBRs. And you would say explicitly that that is your slow step, because H2 and Br2 are in the rate law. They are probably the collision that slows this whole thing down. And perhaps you have an HBr that reacts with an O2 to make, I don't know, HBrO2. I'm just making stuff up. I'm pretty sure that's fake news. And then your HBrO2. Oh boy, if you have two HBrO2s reacting. Again, trying to limit my collisions to two molecules at a time, an H2 and a Br2 making this, an HBr and an O2 making this, two of those making the product that we want. And I guess we would get an O2 out of that as a product as well. I'm literally just making up a mechanism. What matters here is that the rate law corresponds to the slowest step of the reaction. There are the kinds of questions where you are given data about changing this concentration does this to the rate, changing this concentration does this to the rate, and you can get the rate law from that. I would recommend you look up get rate law from table of data, and you'll get a video of me showing you an example of that. Someone's asked for ozonolysis tricks. Probably not going to be able to help you with that one. Ozonolysis in my world is just you breaking a double bond and turning them each into a double bonded oxygen. A fluxational molecule is one that undergoes a dynamic molecular process that interchanges two or more chemically or magnetically different groups. What does that mean? A molecule is fluxational if its spectroscopic signature exhibits line broadening. Wow! Methanium CH5+. Oh my lord. NMR spectrum shows only one signal for each of the methyl groups. Near room temperature, separate signals are seen. The rate of exchange can be readily calculated at the temperature where the two signals are just merged. This is coalescence. I have no idea. Nope. Man, maybe I should have, I'll take questions ahead of time next time, maybe, eh? Fluxational molecule concept. Never heard about it in my life. Will have to learn it on my own. Ring whizzing? The heck? Never heard of it. I don't know. I'll try to learn it. Sorry to those of you who are asking about that. Okay, I'm going back in the chat here. We've got a bunch of people speaking in a language that I admittedly do not understand. Someone talking about gangbangs. Hello, people. Will we be able to access? Can you simplify molecular orbital theory? No. The answer is no, I can't. I barely understand molecular orbital theory as it is. I could imagine myself hiring a tutor to teach me so that I could teach you. You'll notice all my molecular orbitals are just basically drawing it for simple molecules, and usually where the two atoms are the same thing. By the time you get to carbon forming molecular orbitals with oxygen and the atomic orbitals don't line up, I am absolutely lost. We prove the Gay-Lussac's law. Can you explain how to calculate oxidation numbers for molecules in a chemical equation? Yes. Yes, I can. Regards to Thomas Muller? Yeah, sure. Can you explain how to calculate oxidation numbers? Oh, 2 oxidation number questions. Great. Everyone's heaping praise on me. I appreciate that. You're all good people. Are we going to get recorded session? Yes, you will. Can you show an example of how antioxidants work? No. No, I cannot. The theory is that, so antioxidants are the ones that can absorb the radicals. I'll get to oxidation numbers in just a second, but we already talked about radicals, so I will go back to it. So how can you actually absorb this radical in a safe way? The answer is there are some chemicals that can react with it and then disperse the extra energy that the radical provided in a safe way. Is citric acid one of them? Polyphenols are one of them. One of the theories of aging used to be that free radicals inside the body were reacting with your DNA and slowly breaking it down. And so eating antioxidants would help prevent the aging process. I'm pretty sure that ended up being fake news. Antioxidant industrial chemicals. Oh, ascorbic acid. Here we go. So here we've got something. This is going to be your antioxidant. It can react with this OH and I suppose produce H2O. But yes, it does produce a new radical at the end of that reaction. But oxygen gas can also be considered a diradical. And oh no, that's just some, yeah, to tell you the truth, I don't know. Superoxide dismutase is some enzyme that will react with it. I guess that's cool. But I have no idea how it actually works. My understanding is that most of these antioxidants give off the extra energy that the radical caused inside the molecule. by giving off light or heat or kinetic energy of some kind? Nope. How do antioxidants actually work? Great question that I don't have the answer to. Thanks. Sorry, Colin. Yes, we're doing oxidation numbers. Someone's quickly asked why there's 2 valences for Fe. All the transition elements can have multiple arrangements of the electrons that are somewhat stable. It's because by the time you get to the transition elements, you have electrons smeared through 5 different orbitals. The D subshell, the 3D subshell, has 5 separate orbitals that the electrons can be smeared through. And in addition, the 4s orbital, which is a lower energy than 3D, is happy to be either full, that's holding 2 electrons, or half full, that's holding 1 electron. Because it's happy in both of those possible states, transition elements end up having more than 1 possible charge. Antioxidants give away electrons to radicals without becoming radicals themselves. Yeah, you know what? That makes sense to me, but it would have to give away 2 separate radicals, or it would have to give away electrons to 2 different molecules in order to not be left with an unpaired electron. What you're saying makes sense, I just don't have any mechanisms about it to show you and make it more illustrative, you know? Thank you, though, Total Recall 13. Okay. So we're going back to what I consider high school chemistry here, calculating oxidation numbers. Okay. Teachers will often give you rules for calculating oxidation numbers, and some of them end up being true and some of them don't. In fact, some of my early videos, I think, used a simplified way of looking at things. Really not sure. Sorry, I'm just writing a note to myself about the radicals giving away 2 electrons each. The general rules for calculating oxidation numbers are that pure elements have an oxidation number of 0. So, Cl2, both the chlorines are 0. Magnesium, that's 0. Let's do S8 just to mess with you. Pure sulfur, also 0. The rule that teachers usually give is that oxygen usually wants a charge of -2. But then teachers here will say that peroxides are the exception. But then you have to know what a peroxide is, right? So the way that I teach it now is that group 1 elements like having an oxidation number of +1, and group 2 elements like having an oxidation number of +2. Oxygen will take on whatever oxidation number is required so that the sum of all the oxidation numbers is the charge on the particle total. When we say peroxides are an exception, it's like Na2O2. That's sodium peroxide. The Na wants a charge of +1 because it's a group 2 element. The O's would have to be -1 in order for 2 of the NAs and 2 of the O's to cancel each other out and make a total charge of 0. But in all other cases, oxygen's probably going to want to be -2. For example, in H2O, the O will want its charge to be -2. We say that O's oxidation number is -2. Come on. There we go, -2. And then each H, of which there are 2, is +1. Note again that 2 of these combined with 1 of these would give you an overall charge of 0, the total charge on the molecule. There we go. Nuts. There we go. We'll get to more advanced examples in just a second. Hydrogen similarly likes having a charge of +1, but teachers here give you an exception to that as well. A hydride, which is a hydrogen bonded to a metal ion, are also exceptions. NaH, sodium hydride. Again, Na wants a charge of +1. And I teach that rule right off the bat so that we look for our alkali metals and alkaline earth metals first. The H in this case needs to be -1 because NaH is a neutral compound total. So what I'm doing here is I'm working my rules from most important to least important. If it's a pure element, it gets a 0. Pure sodium, for example, has an oxidation number of 0. But sodium likes having an oxidation number of +1, and anything attached to sodium will take on whatever oxidation number is needed so that the sum of the charges, the sum of the oxidation numbers is the same as the total charge on the molecule. After you deal with hydrogen and oxygen, I generally just tell people that other atoms take on whatever charge is needed. Oh, come on, computer. Other atoms take on whatever charge is needed so that the sum of all the oxidation numbers is the total charge on the particle. Someone has talked about, someone said formal charge, question mark. I don't know if you mean you want me to go over formal charge or if this is related. This is actually not related to formal charge in my experience. Okay, but you want some nuts and bolts, right? Na2Cr2O7. Here's sodium dichromate. This isn't a pure element, so we're not going to deal with this first rule. But there is a group 1 element in there somewhere. So I would start by saying that each of the NAs has an oxidation number of +1. That's the most important rule in my book. There are no group 2 elements here. There's no hydrogens here. So I'm jumping down to oxygen usually wants -2. Oxygen is not the last thing here. So all of a sudden, it can have a charge of -2. Oh, someone's asked for me to share this document. Yeah, let's do that. I've already shared it with everyone online, but I haven't, whoops. I'm going to go over here. There's your document if you want it. Thanks for the question. That was useful. Okay. Sodium is +1. Oxygen is -2. Now there are 2 sodiums here, so that contributes +2 total. That is +1 for each of the 2 sodiums. And there are 7 oxygens. That contributes -14 to the total charge, because I have 7 of them and they're each worth -2. That means that the chromiums must be something, so that their total contribution is the difference. -14 can partially cancel with the +2, but you still have another -12 that needs to be neutralized. You need +12 total from the chromiums so that the total charge on this particle is 0. And there are 2 chromiums across which to distribute that +12, so it becomes +6 each. And you can determine here that the oxidation number of chromium in this particle is +6. Highly oxidized. I'm going to do one more example here. I'm going to do NO3 with a minus charge on it, like a charged particle. This is an ion. The total contribution needs to be -1 in the end. There's no pure elements here. I've got nitrogens and oxygens. There's no group 1 elements here. There's no group 2 elements. I guess most of the time I actually call this metals. There. There's no hydrogen either, but oxygen usually wants a charge of -2. So if each of the oxygens has an oxidation number of -2, oh Lord. That's -6 total because I have 3 of them. What's the oxidation number on my nitrogen? Well, I need the sum of these contributions to be -1, not 0, -1. Therefore, this has to contribute just +5. Note, the sum of those contributions is -1, which is the same as the charge on the particle. That's like the trick here. Nice. There's only one nitrogen, therefore it's +5. Nitrogen, on the other hand, can have lots of different oxidation numbers. Here we have N2O. Oxygen likes to have a charge of -2. That contributes -2. The nitrogens need to contribute +2 total, but there are 2 of them. Therefore, each of the nitrogens has an oxidation number of just +1. Yes. Now, the whole point of calculating these is that in chemical reactions, you might have one thing get oxidized and another thing get reduced. By that, I mean the oxidation numbers will change. Not sure I can come up with one of those right off the top of my head. The one that I like the most is usually like, wait, let's just do this. Na2CR2O7 plus N2O becoming NO3 minus 1 charge plus Na. Sure. And chromium. What does chromium become when it gets reduced? I should remember this, but I don't. CrO2? CrO3 with a -2? Something like that? I don't remember. Anyways, the point is that this Cr has an oxidation number of +6, and then it gets reduced to +4 here. Nitrogen starts at +1, but its oxidation number grows to +5, so it is getting oxidized. It's actually called reduction because it's the oxidation number that is getting reduced. And so the N is going to go from +1 to +5. The way that I've written this, it is the N that is oxidized. Now officially, that means that it's N2O that is the reducing agent, because that's where the nitrogen is that is oxidized. And Na2Cr2O7 is the oxidizing agent because it contains the atom that is getting reduced. It's one of those little mind twisters in case you're being asked about reducing and oxidizing agents. I feel like I've answered that question. I've got a set of rules here that I use when I'm calculating oxidation numbers. Okay. What do we have here? Thank you to those of you who are answering questions for me. Total Recall 13, you were very helpful with the antioxidants. Someone asked what a precipitate is, and someone has explained it, I think. A precipitate is a solid that is made over the course of a chemical reaction. And it is usual. Oh, come on. Solid created in a chemical reaction. I hear the word precipitate usually from aqueous reactants, but I suppose you could have a solid falling out from a gas. I suppose you could have a liquid falling out from a gas as well, and we might call that a precipitate, but we'd usually call it something more specific, like a condensation of some kind. Lead 2 nitrate, for example, does dissolve in water. So we tell people that by writing AQ as the state. When you dissolve it in water, it's a clear, colorless solution. Kind of looks like pure water, except it has lead in it, so you shouldn't drink it. Potassium iodide is the same. When you dissolve potassium iodide in water, it's a clear colorless solution. The potassium and iodide ions have dissociated and they've dissolved in the water. But potassium and iodide cannot coexist in aqueous solution at the same time to any significant degree. So they get together to form a solid ionic compound. It is that solid that is produced that we call a precipitate. It's called a precipitate, presumably because it will slowly fall out of the water and form a little powder on the bottom of your test tube, kind of like rain falling out of the atmosphere when it rains. That's it. If you're asking about precipitates, you're probably looking at double displacement reactions between two aqueous ionic compounds. Okay? Okay. I think the amount of substance removed after a reaction is called the precipitate. So, to mighty study, you're kind of right. Most of the time when teachers are talking about precipitates, they're either straight up asking you what it is to know that you know what it is, or they're asking you about the mass of precipitate that's made. Here, I could have given you initial concentrations and volumes for each of these two things. Get the limiting reactant, figure out how much PbI2 is made, but then if you poured that mixture over a funnel with filter paper, all of the water and KNO3 that's dissolved in the water go through the funnel and filter paper, but the PbI2 is left over. It's solid, it doesn't dissolve, it's what's left. And so it's the thing that in the lab is the easiest thing to measure of this chemical reaction. Why can't we contain a nuclear fusion? I assume the answer to that is just so much energy is produced that it will catalyze a runaway reaction. Like one thing reacts and it gives off enough energy to make the next molecule down the chain react, and then it causes the next thing to react until they're all reacting at the same time. It's like a runaway chemical reaction that you cannot stop, like a forest fire, except on the atomic level. I can't prove to you that we can't do that. Why can't we contain nuclear fusion? That sounds like a Vsauce video if I've ever heard it. I need help understanding what Gibbs free energy means. Okay, I'm not gonna lie to you. I got through my entire chemistry degree simply believing that Gibbs free energy is something that scientists made up. When you're trying to figure out if a reaction is spontaneous or not, hold on, let me copy and paste that. The person who joined me at the beginning and asked about quantum numbers, when I started off my quantum numbers video, it's basically me saying quantum numbers are made up so that we can explain why the electrons are arranged in a certain way. I look at Gibbs free energy the same way. When you're trying to figure out if a reaction will go forward, oh my goodness, will go forward, which is what we call spontaneous, or backwards, which is what we call non-spontaneous. We use Gibbs free energy to make that distinction, and we call it delta G. But what you're really doing here is tying together enthalpy considerations, which is energy stored inside of chemical bonds. I'm going to change that because it's not like you break a bond open and get energy out. It's the energy change of forming or breaking chemical bonds, as well as this new concept that teachers usually bring up at the same time called entropy, which is a measure of disorder. And it's basically second law of thermodynamics. The whole world just tends towards more disorder. You can spend your time stacking things up into a pile, but the natural order of things is them for all to be scattered on the ground as far apart as possible. Entropy itself is an obscure measure of how disordered a system is. And there isn't really, to my knowledge, a better way to let kids use entropy to predict spontaneity than simply bringing it up that way. You can calculate the amount of disorder in a system, but that is usually second or third year university. Gibbs free energy is the way you tie these two concepts together to make up the spontaneity concept. Enthalpy plays a role. Entropy plays a role. Sometimes they work in the same direction. Sometimes they fight against each other. Gibbs free energy helps you determine which one is most important in terms of spontaneity. So my answer is Gibbs free energy on its own is not like, it doesn't have any explicit meaning. It's a way to combine enthalpy and entropy to help you predict whether or not a reaction will go forward or backward. Let me know if that answer was satisfying for you. It may not have been. Someone has asked for what I consider a physics question. A 350 nanometer light passes from air through water. What is the new wavelength? Can't answer that. I actually do know how I can help you, though. Then we got something about molecular shape. Oh, that could be a 2-hour one on its own. Change in wavelength, change in based on the refractive index. The refractive index is a measure of how much slower or faster molecule or light can travel inside of a different substance. This is loading. Excuse me, can you help me understand about molecular shape? Yes. It's called reduction because oxidation number is being reduced. Yes, that's true facts. Aldol condensation mechanism. J.R. Malat. I have a video about it, but I don't remember any of it. Like, I was learning it. I learned it and made you a video about it that I posted on my channel, but I don't have any idea what it even is. No idea. Concentration of solutions problem, please. Lajpat, I need you to, if you have a question in front of you and you could, like, type it out, that'd be ideal, but, like, concentration is too wide of a thing for me to help you with. Yeah, someone else has asked for Aldol. Yeah, I got bad news. I don't know it. BOD. BOD, like biochemical oxygen demand or something? Yeah. I learned that at one point, but I don't know if I... Does this stream cover organic chemistry? The answer, you know what, should be no. Aptua, I will create a new stream where I try organic chemistry stuff. And you know what? The people who are asking about aldol condensation, I'll just do another stream, maybe even tomorrow, and I'll brand it organic chemistry for you, okay? My phone's battery is low. I'm going to connect to my computer. My English. Oh, this is a lot of text. I am not mega smart, but thank you. I can Google anything. All substances have a tendency to minimize their Gibbs free energy at constant temperature. Why does this happen? That honestly just sounds like a law of thermodynamics. It just sounds like there's a general rule that we've noticed is always true, and we invented Gibbs energy to represent that thing that is always trying to be minimized. I honestly feel like the answer to your question, Pankuri, is God. God, like, that's just the way it is. I don't know. Yeah, we got a lot of aldol questions here. I'll circle that and do an organic stream tomorrow for you. Thank you. Short inductive and mesomeric effect? I don't know that either. Nope. I'll look it up for tomorrow, but I can't do it. Yeah, if you have organic questions, throw them into the chat here, but I probably won't be able to answer most of them. Wow, this still has not loaded. My life is in shambles. Okay, so it looks to me like that is not what I was hoping for. Yeah, lots of people are done. I understand. Thank you. I don't want why is it different. I just want a formula. Hook me up. There we go. That's what I'm talking about. Okay, so someone asked about how the wavelength of light changes when you go from one chemical into another. Honestly, I consider this physics, not chemistry, but I figured it was going to be fast. So, what we're being told here is that the initial wavelength, or lambda 1, in air is 350 nanometers. Let me go get a lambda. That's not lambda. Anyone see lambda hanging out in... Oh, there it is. Hook me up. Great. We're being told that the initial... Don't capitalize lambda. Get out of here. The initial wavelength is 350 nanometers. And because it's going from air, that means that N1, or the initial refractive index, is about 1. You might have 1.000 whatever. That's the way it goes. If you have a more accurate number for the refractive index in air, use that. You don't know what the second lambda is, but you do know what the second refractive index is because it says it's going through water. I believe water has a refractive index of about 1.33. Thus, you can plug each of these numbers into the formula and we'll solve for lambda. N1 is 1. The initial wavelength is 350. We are going into 1.33 as a refractive index, and we don't know what lambda 2 is. In order to solve for that lambda, you're going to have to divide both sides by 1.33. You can do it on your calculator. 350 divided by 1.33. It gives me 263-ish nanometers. But it's just a formula, kind of like Snell's law with the angle of refraction. The angle of refraction changes because of Fermat's principle, and the light wants to take the fastest route from one place to another. Wow, everyone's excited for organic. Do I have any commitments tomorrow? No, I don't think I do. I can just sit online and help with organic chemistry. Yeah, someone just gave me the answer, 263.157. I like it. I like it. Organic stream will be tomorrow. Yes, yes it will. Thank you, everyone. There you go. There's my word to you. Okay. Someone asked about molecular shape. Someone said, would you be able to go over different types of titrations? Ooh, okay. Here we are. So we're going to do molecular shape. We're going to do titrations. We're putting off all the organic until tomorrow. Coming back after a couple years to your channel. Good to have you with us. JEE. Everyone talks about JEE in India. I should download some of those. Some of your questions are insanely difficult on that. No, well. Okay, I'm back. Okay, so I'm going to do two more. I'm going to do molecular shape. I'm going to do titrations. And then I think I'm going to log off. Pearson acid-base theory. Yeah, okay, I'll Google that. I've never heard of it in my entire life. Great. Okay, so I'm going to call it there. Molecular shape. Okay. Everything I know about molecular shape comes down to drawing the Lewis structure and then seeing how far apart the lone pairs and atoms can get away from each other to determine molecular shape. My personal thing for this is to draw the Lewis structure. Hopefully you guys know what Lewis structures are. It's the bread and butter of my channel. I can do a couple with you. The question I ask myself is how many lone pairs, like lone pairs of electrons, are on the central atom? Now that's the very center of the molecule or particle. And I ask how many atoms are connected directly to the central atom. With that, I can figure out how far apart these things can get. And all of them are based off of how many things are attached to the central atom. What I mean is, when I say the word thing, yeah, someone's talking about Vesper. Yeah, we're getting to Vesper, don't worry. When you have two things attached to the central atom, be they lone pairs or atoms, they will arrange themselves in a linear way. How far apart can two things get around a center? The answer is pointing in opposite directions or linearly arranged. If you have three things around the center, those will be arranged in a trigonal planar manner. Now, I'm not saying the molecule's trigonal planar. If there's a lone pair, that generally doesn't contribute to molecular shape. But the question is, how far apart can three things get? The answer is 120 degrees away from each other, still surrounded in a circle. If you have four things, they will arrange themselves tetrahedrally. Again, lone pairs will also help to influence the actual molecular shape, but the lone pairs will arrange themselves tetrahedrally. Five things we call trigonal bipyramidal. It is one thing up top, one thing down below, and then trigonal planar around the center. And then lastly, we have six things. If you have six things connected to your central atom, those will be arranged octahedrally. Now, I say these things, I know what they look like, but I've been in this game forever, right? So, trigonal planar tetrahedral octahedral. Let's see if I can get an image about this. Yes, yes, yes. That's what I'm talking about. Copy. Oh, I'm really having trouble because I don't know what I'm doing. Yes. Okay, this table is kind of what I tried to summarize. And when I said what I said, I was really just dealing with the first column. When you have five things around a central atom, they're going to arrange themselves this way. One up top, one down below, and then three things in a circle around it. Octahedral is one thing above, one thing below, and then square planar around it. X here represents whole atoms, like not lone pairs. E's, capital E's, represent lone pairs here. And when I say that I want you to figure out how many lone pairs and atoms are on the central thing, here we have a central atom with two atoms and one lone pair. That's three things, so this molecular shape, like the whole electron arrangement, is trigonal planar. But this E is like empty. There's no atom there, no nucleus there. It's just electron density, so it doesn't really contribute to the molecular shape. Thus, you can kind of ignore it. I'm going to scroll up just enough that it looks like the A and the two X's are all that's there, and we call it a bent molecule. You kind of have to memorize these names unless you're going to be given this chart. The VSEPR notation is capital A, capital X, subscript however many X's there are, or however many atoms are connected to the central atom. Here's what I mean. Up here, when I said draw the Lewis structure, how many lone pairs are there? How many atoms are there? Each lone pair is called E in VSEPR notation. Each actual atom that's connected is X. Okay, let's do an example so that no one feels like I'm leaving them out to dry here. I'm going to do the one that I think is among the toughest. XeO F2. It is a xenon atom with an oxygen and two fluorines. Let's go get XeOF2's Lewis structure. Wayne Breslin's got it covered for us. Okay. When you draw the Lewis structure, it ends up being something like this. Xenon brings 8 valence electrons with it. Oxygen brings 6, fluorine brings 7. So xenon contributes 1 electron to each of the 2 fluorines, 2 electrons, well, actually in this case, maybe 1 to the oxygen. I don't like that formal charge, but whatever. And you have 2 lone pairs here. It's the Lewis structure that will help you figure out what's on your central atom. Your central atom is A. How many atoms are connected to the central atom? Well, you have 2 F's and an O. That gives you 3 atoms connected. And how many lone pairs are on the Xe? According to this diagram, it is 2. So we're going to call it AX3E2. Now the way I think about that is that that's 5 things total. How far apart can 5 things get? It's trigonal bipyramidal. 1 up, 1 down, and 3 around the center. Let's see if I still got it here. 1, 2, 3, 4, 5. 1 up. No, let's do the 3 around the center first. You can see here on my camera, I've got my 3 things. Can you see that? Oh, you can. It's just that everything's reversed. I got 3 things all separated by 120 degrees. I'm going to take an extra one, put it on top. Take another extra one, put it on bottom. There's trigonal bipyramidal. But we have 2 lone pairs here, not 5 atoms. So you take away 1, 2 of those, and you see what shape you're left with. Here I have a T shape, and that's also what it's called here. Where am I? What it's called here. You're starting with the same structure, but then you're chopping off 2 of the X's because they are lone pairs. Lone pairs do not contribute to molecular shape. They just don't. Now, I've seen some people say that the 5 things, including the lone pairs, mean that there's an electron geometry, and it's trigonal bipyramidal, aka there are 5 things. But what you're asking about is molecular shape, or Vesper shape. And it's T-shaped because that's trigonal bipyramidal without 2 of the extra X's. Oh, that is not what I meant to type. There you go. So, your job is going to be basically to memorize these 5 in this column. And then you can simply pop X's off, keeping the geometry the same, to get the actual molecular shape. Very nice. What is sharing electrons? I don't get it. Are we talking about XeOF2, Mayer? Someone's asking about B in B2H6. Yes. B2H6 is a special molecule where each of the H's are connected to each of the B's. Yeah, it's a covalent bond that they're sharing electrons between. Thank you, name that I don't know how to pronounce. Is it square planar? No, it is not. It is T-shaped. Although it is planar, like this T can lay flat. it is not square planar because there was no fourth thing. Hard acids and hard bases. I'll deal with that another day, I believe. Hard and soft acids. Yes, I can create something about that, but I don't know it off by heart. Someone has asked for titrations. I just learned it from my online classes. It's an interesting concept. Oh, cool. You're all go-getters, eh? That's pretty cool. Okay. Yeah, so if you're... I'm going to do something about titrations. I'm going to look up Pearson acids and bases because someone asked about it, but I don't know anything about it. And then I'm going to call it a day out here. Tomorrow, same time probably, I will do an organic chemistry stream. Let me say, though, I am not good at organic chemistry. I can help you with some things. I know alkene reactions. I know esters. I know enantiomers. But you are going to be able to punch holes in my knowledge pretty aggressively. Maybe I'll invite a friend on, a friend who might know more organic chemistry than I do. We'll see. Pearson acids and bases. Huh, it suggested it in Spanish. Though, to the person who asked for titrations, I have not forgotten about you. Oh, Pearson is hard acids and soft acids. It's for explaining the stability of compounds. Oh, boy. There is so much I don't know. Nope. Nope. Can't do it right now. Sorry, those of you waiting on Pearson stuff, I got nothing for you. I helped someone with their MCAT. Hey, that's great stuff. That's excellent to hear. Is Hess's Law organic chemistry? No. Hess's Law is definitely like high school inorganic chemistry. Julia, paste your questions into the chat and I'll just make you a video this afternoon about it. Yeah, Gen Chem, that's the word. Thanks. Okay, so the last thing we want to do here is titrations. Well, that's the last thing I'm going to do. Thanks for being with me. It's been 2 hours. I don't know how long a Twitch or OnlyFans stream normally goes. Let me know if you want an OnlyFans from me. Okay. Okay, so here's the deal with titrations. You're generally starting with an acid or a base, and then you're adding the opposite kind to it. Starting with, well, I guess it's not pure, but you are starting with only aqueous acid or base. Oh my lord. Someone's laughing at me. That's fine. This computer's from 2017. I guess it's lag and hard. Oh well. You're going to be able to calculate the pH of something like that from regular acid dissociation. Like the concentration of the H plus at that point is probably just the square root of the concentration times the Ka. Now, there are other ways of doing that. An ice table for equilibrium might be required, but you're basically just saying, I am starting with this acid, here's what the pH is, whatever. Then you're going to add a small amount of base. Or acid if you started with base instead. All of a sudden, you now have some H+. Obviously, if you started with acid, you have some H+. And you probably have some of the conjugate base. let me see if I can reword that here. Some acid and some conjugate base. Conjugate. You know what? Let me just shuffle this over a little. Insert table. The 90 minutes helped me out a lot. Oh, nice. Thank you, Siddhartha. I'm gonna have to put my computer in the freezer after this. Okay, let's say we're starting with CH3COOH, acetic acid. That is a weak acid. We'll do a weak acid and a strong base just to start. You'll start to see the pattern in just a moment. I'll use NaOH because it's classic as well. And I don't think I need these, so I'll delete those. Someone says hello, bro. Okay, so at the very beginning of your titration, you have just your aqueous acid, and for example, it might be CH3COOH. Now I know that when you put a weak acid into water, you already have some of the conjugate base, but all you really have to know is the initial concentration of the acid. The next major point in a titration is getting halfway to equivalence. And that's because you've therefore titrated away half of all the acid. So you have half of the aqueous acid remaining in solution, and half has been converted to its conjugate base forcefully, as in the NaOH forced the CH3COOH to become CH3COO-. If I was to list that here for you, we'd still have some CH3COOH in solution, but now we have an appreciable amount of that same thing deprotonated, aka its conjugate base. Now, when you have the same amount of original acid left over and conjugate base forcefully made, this is actually called, I think it's called the buffer point. And in order to figure out the pH at this point, you can use the Henderson-Hasselbalch equation. Someone's asking me where this is going to be. I believe it's going to appear on my channel. So you just go to the channel and then there will be live streams there. I'll see if I can create a category for you. You should be able to find it. I don't have a better answer than that. So, at the very beginning, you have only acid. Again, some of the acid will hydrolyze or dissociate in water, but I want you to think of it as just the acid. Then as you add base, some of the acid is forcefully getting converted to its conjugate base. Halfway to equivalence, you have half remaining of each, or rather, half of the acid has been forcefully converted to the conjugate base, so you have both, and now you have a buffer. The next most important point is called the equivalence point. Here, we say we have none of the aqueous acid remaining. None of the aqueous acid remains. It has been fully converted to its conjugate base. So you can consider it the solution to only contain CH3COO minus. If you go past the equivalence point, you'll have the conjugate base, and you're going to have excess OH minus that had nothing that it could have reacted with. There's no acid remaining. And so the thing that's going to control the pH in that zone is actually the OH minus that you've added on top of what you needed to get to equivalence. Is the equivalence point and buffer point the same thing? Hell no. No, no, no. Unless I'm wrong about what buffer point means, I guarantee you I'm not. I'll even show you a picture. Yeah, your teacher's wrong. Take a look. Oh, this is exactly what I'm doing right now. I want this. Give it to me. The equivalence point is a point along that vertical line in the titration curve. The buffer point is exactly halfway horizontally to the equivalence point. If your teacher was doing that, saying them interchangeably, they are wronger than I've ever heard in my entire life. But hey, what if I add some salt on mineral water? I'm not gonna lie, I don't know. Like, probably nothing, if you ask me. Don't be an SVG. Thank goodness, it's Imgur. I love you, Imgur. Okay, here we have only acid. Here we are halfway to equivalence, so you have some of it having been converted to its conjugate base. Only half of it, though. So you have some of the acid left. You have some of the base that's been forcefully created. Equivalence point is when you've forcefully converted all of your acid into its conjugate base. You've added as many OH minuses as you had of acid before. In fact, I'm going to write that in here. You've added as many OH minus. Oh my lord. You've added as many OH minus ions as you began with CH3COOH. So you have the same number of OHs having been added as acid particles that you started with. The mineral water is bubbling when you add salt to it. Oh, it's probably, I don't know. Now I want to point out that this buffer point exactly halfway to equivalence, the pH at that point will happen to have been the pKa. That comes from the Henderson-Hasselbalch equation, which, by the way, is what you use to calculate the pH in any of this region except the beginning or end. Anywhere else along here, the Henderson-Hasselbalch equation will work for you. if you've seen the Henderson-Hasselbalch equation, you know that there's a log in there somewhere. That's why this looks like a log function, and actually this one looks like an exponential curve as well, or an inverted log function. Whatever, no teachers ever asked that. And then here, you're just adding OHs, so you get super basic. I want to point out one more thing. The fact that you have this little wisp at the very beginning, before you flatten out, is what tells me you started with a weak acid. If you'd have started with a strong acid, this would have been a straight line. It might have been tilted upwards a little bit, but you wouldn't have had this S-shaped curve before the equivalence point. Let's see if I can find one like that. Well, that one has the wisp, so it's weak acid as well. Weak acid, weak acid. Well, these are all boring. Oh, it's because there's no buffer for a strong acid. Strong acid, strong base titration curve. You'll note it does not have that S shape here. It simply starts and goes linearly from there. If you start with a weak acid or weak base and you add acid to it, it's going to be the same thing but vertically flipped. You're going to start up here at 12 or 14, and you're going to come down. If you started with a strong base, it's straight across. If you started with a weak base, there's that wispy bit. There's a buffer point in here somewhere, equivalence, and it continues on. I'm the person who asked about titrations. I struggled in this unit. Okay, it looks like we have a lot of good stuff. Thank you everyone for your feedback. I got feedback that the 90-minute thermo was helpful. I should just make 90-minute videos about all these topics then, right? And importantly, I've learned many of you are studying for a JEE. I didn't even expect a bunch of you to be studying in July anyways, but here, whatever. You can always ask me questions whenever you want. I'm on Facebook, I'm on Twitter, I'm on YouTube. I think my community tab is open so you can put things there. I read these things to get ideas for my next videos. So feel free to ask me stuff whenever you want. There were lots of questions I was not able to answer. I will try to teach myself this stuff later. Tautomers, zeolites, fluxational molecules, how antioxidants work, BOD, biological oxygen demand. That's in my mind somewhere, but I need to refresh myself. Pearson acid-base theory for hard and soft acids, and general JEE chemistry. Tomorrow, I will do a stream for you by request of only organic chemistry. I cannot promise you that I can answer any of those questions. Organic chemistry is my weakest point, I think. I teach high school chemistry, so I know some of the easy reactions. But the professor who taught me my third organic chemistry class, we couldn't understand him. He was not a good teacher. In fact, the day we wrote the final exams, he flew off back. He went to China and just never came back. A bunch of kids couldn't graduate that year until October, when he just came back and got reprimanded for running away with all of the marks and exams. Anyways, organic is not my strong suit, but I will help you with it tomorrow. I promise you that. Thanks for being with me. And again, if you have more questions, get at me anytime you want. I'm free all summer. I'm going to stick around for a couple minutes. We can just shoot the breeze, but I'm not doing chemistry. Besides steric effects, are there any reasons why nitrogen iodide explodes? Nitrogen iodide explodes, I think, because of Gibbs free energy more than anything. Like, it wants to be exploded. It just needs a little bit of energy input to make it happen. Don't quote me. Can you use Henderson-Hasselbalch for all types of titrations? No. One of the things has to be weak for you to use Henderson-Hasselbalch. You have to start with either a weak acid and be titrating with a strong base, or you have to be, actually, as long as one of them's weak, or both of them are weak, as long as one of them's weak, you can use Henderson-Hasselbalch. But you never do use Henderson-Hasselbalch at the very beginning or at or past the equivalents. You have to have added some acid or base to the initial acid or base before you can use Henderson-Hasselbalch. Mustard sauce has a great username. I know this feeling. I had the exact same situation trying to learn by myself. Molarity and molality problems with density. I can do a video about that and post it for you. Monohalides and dihalides. I have a video about that. I just don't know where it is. It's possible that it's like unlisted. I'll write a note to myself so that I can remember to post it. Please help me with a trick so I can remember the D block elements easily. Wait. You have to memorize the D block elements? Is that what I'm hearing? Here in Canada, we never make kids memorize that. You can just look it up. You can just walk around with a periodic table and all of a sudden you don't have to memorize it. Lajpat, I wrote your name instead of the word I wanted here. I can do like a 90-minute mega video about titrations at one point. I can try to crank it out today. Please help me with a trick so I can remember the D block elements. You have to memorize the whole periodic table. Oh boy. I do have an idea for you. Oh boy, sorry guys, this looks ugly for you. I'm just fiddling with my streaming software so you can know. There. There. Yeah, everyone's like, wow, that sucks. Sucks to be you. For NEAT, you need to memorize in the whole periodic table. Are you memorizing numbers as well? Hi, he, Libib Kanafni. My dad used to tell me like there was a song about it. And it was like, hi, he, Libib Kanafni. And then you like make up this rhyme that carries you through all the elements in order. Okay, if you need to memorize the whole periodic table, you're better to go on like sporkle.com. Sporkle.com is like an online quiz thing. You don't want geography, movies, or music. You want to search for periodic table. Let's see what we got here. I've never actually done this. Oh, none of these look particularly good. Please be arranged in the actual periodic table. It's processing. Oh, watch Arvind Arora's video. Arvind, I'm writing that down. Arora. memorize periodic table. I'll look at that. Oh yeah, this is what I'm talking about. So it brings up the table, right? And you have 15 minutes to go through the whole thing. And if you're trying to test yourself, you just go through the ones that you want, right? So we all know some easy ones here, like hydrogen. Wow, this is really slow. Helium. Great. But you're talking about the D block elements? Pfft, I got nothing for you. I know what they are, but it's only because I've used the periodic table so often. Scandium, titanium, vanadium. I'm remembering these ones because of the charge that they have. Sc is +3, Ti is +4, V is +5. Then you have chromium, which we saw was +6 later. What comes after chromium? I don't know. No idea. Iron is in there somewhere. Nope, I missed one. Copper is later. Zinc is in the first one. Yeah, I got nothing. I have no idea. Anyone want to help me with that? What comes after chromium? What can be +7? Technetium is under that. But what's above technetium? Manganese. Manganese. Thank you, Havish. Wow, you guys are all heroes, and I'm a loser. Oh, cobalt is in there somewhere. I don't know. I'm blanking on this last one too. It's not gold or silver. Where's my periodic table that I can cheat with? Okay. Well, whatever. Honestly, it breaks my heart that you have to memorize the whole table. But that's the way it's got to go. Arvind, nickel. Thanks, everyone. I'm on a massive lag with you guys right now. If I look over here, stream health. My stream status is poor. YouTube is not receiving enough video to maintain smooth streaming. Oh well, what can you do? Okay, good stuff. I think I'm logging off here. Thank you very much for being here, everyone. I will go through all of your chats. Take a look at your questions, try to crank out some videos for you. I'm going to publish a live stream notification or whatever for tomorrow. We'll try organic chemistry. I cannot promise that I can answer anything. Fecko Nico. I like that. I like that. Please explain what an acid-base buffer is. It's when you have some acid and some of the conjugate base in the same solution at the same time. Thank you for being here, everyone. It's been 2.5 hours, so I'm just gonna take off. I do appreciate you being here. My YouTube, Facebook, and Twitter are always open for questions. I'm also on Reddit. It's chemist__Nate, and you can just message me there. Whatever. Thanks, everyone. I appreciate all of you, and I'll see you some other time.